Okay guys, so in this video we're going to talk about the integral test and estimates of sums. So let's first talk about that as a concept. So in general, it's actually really hard to find the exact sum of a series. As a reminder, sums are, we're taking the sum of some sequence, a sub n. A sub n would be a sequence of terms. The sum of it adds them. X amount of terms, however we want, and a series is the infinite. So like n equals 1 to infinity, that would be the series. So finding this infinite sum, or series, is actually kind of hard because we're adding infinitely many values, and a lot of times it takes quite a lot of thought to go into trying to find the exact value. We can solve geometric series because they have nice formulas for finding this nth partial sum. But usually, however, it isn't easy to find such a like a formula. Like geometric series are an oddity in that regard. So what we've done is develop tests that allow us to determine whether a series converges or diverges. Because if it converges, then we can add it to a value. If it diverges, then it just goes off into the infinite. That is, you're adding infinitely many values and it goes to infinity, so we know not to waste time trying to find this infinite sum, this series, because there's no point. It goes to infinity. So we only waste time trying to find it with the convergent series, and also we actually have found ways to find pretty good estimates of it. Basically, we can find an estimate that's as good as we want it to be. So if all else fails, if we can't think of some clever way to find the exact value, we don't really need that. We can just find an approximation and make it as good as we want it to, because we can also determine our error on that approximation. If we're not happy with the error, we just do a better approximation. Okay, so what we're going to use is this thing. It's called the integral test. Now, the integral test is kind of the basic test to test whether a series converges. But it involves the integral, as you'd expect. And one of the problems with that is, as we know from Calc 2, obviously, is that integration can be challenging sometimes. So if we end up with a series that is something we can integrate, then cool, we'll use the integral test. But if it's something we can't easily integrate, we'll use other methods that we'll learn in this chapter. So anyway, suppose f is some continuous positive decreasing function on the interval 1 to infinity. So what that means is, in terms of, if we're thinking about this function, it would look something like this. Okay, it's all positive, it's decreasing from 1 onwards. Now, technically speaking, this isn't a necessary requirement. It could actually be decreasing just after some point, but we often call it 1. So for example, what I mean by that is we could also have had something that maybe goes up for a bit and then decreases the rest of the time and stays positive. I know that doesn't look like it stays positive, but trust me, it stays positive here. Then that's actually okay. So this isn't a complete restriction, but just something to be aware of. Anyway, it's a continuous positive decreasing function on some interval to infinity with a sub n equal to f of n. So our sequence is equal to f of n, where n is a natural number. Then the series from n equals 1 to infinity, again the infinite sum, our series of a sub n, is convergent if and only if the improper integral is also convergent. So when we see this if and only if statement, what that means is it's true both ways. So the way it's written, if we can show that we have some series is convergent, then the improper integral is also convergent. But more importantly is that if we can show that this improper integral is convergent, then our series is convergent. And that's what an if and only if statement means, is that we can read it either way. So if it's easier to show that this is convergent, then we can show this is. If it's easier to show that this is convergent, then we can show that this is convergent. And in general, we're kind of starting here. So if our improper integral from 1 to infinity, or really our n to infinity, whatever value it starts to decrease at, is convergent, then our series here is convergent. And if our improper integral is divergent, then this series is divergent. So we're going to use integration to find this thing. All right, so let's take a look at that as an example. So determine whether this series from n equals 1 to infinity of n to the negative 3 is convergent or divergent. Now, this thing here, if we think about it in terms of f of n is a sub n. So let's just rewrite. That's 1 over n to the negative 3. That's what this, excuse me, to the 3. I wrote it on the bottom for a reason. Okay, so this is our function. So basically, what it says we need to do is we need to take the improper integral of this function from 1 to infinity. And often it says we're doing it in terms of x just because we're used to integrating with respect to x, but you can do it with respect to n too. I mean, there's nothing that says you can't. Whatever variable we want, who cares? Okay. But this is officially what we're doing, is we're taking the integral from 1 to infinity of 1 over x cubed dx, because that's what this series is. And if we can show that this converges, then this is convergent. Okay, so if you recall, our improper integration is the limit as t approaches infinity, or any variable, it doesn't really matter, of the integral from 1 to t of 1 over x cubed dx. So we're going to integrate this thing, and it's probably easier in this form. Increase it by 1, so that would be x to the negative 2 divided by negative 2. And we're going to take this from t to 1 here, and we're going to say the limit as t approaches infinity. Okay, so plugging this in, we get negative 1 over 2t squared minus negative 1 over 2 times 1 squared. And we're going to take the limit as t approaches infinity. Okay, so plus or minus a negative is plus a positive. As t goes to infinity, 1 over 2 times infinity is just going to be negative 1 over infinity plus 1 over 2. And negative 1 over infinity, this is just 0, because a constant divided by infinity is 0. So that means that this improper integral here converges to 1/2. So because it converges, then the series converges. So our series is convergent by the integral test. That's what we would say. The series converges by the integral test. Okay. So that doesn't mean that the series converges to 1/2. Like it's not that if we add this up, it's 1/2, because it isn't. That would be the infinite sum. That's adding infinitely many points, and it would be 1/2. But what we're doing is we're adding in a series individual values. So technically speaking, it's still infinitely many, but just to show you what I mean by that, 1 over x cubed, when we're integrating it from 1 to infinity, okay, we're finding the area under this curve as a reminder. So from here onwards, the whole area under the curve. However, when we're talking about series, okay, what we're doing is we're only taking our natural number of x's, so and adding those values together. So what I mean by that is at 1 we have 1, at 2 we have this value 0.125, at 3 we have this, and 4, 5, 6, 7, 8. And what we're doing is we're adding 1 and this and that and this and that and so on and so forth. And so we're pretty much just taking those individual terms, not every value along that way. Okay, so That is kind of the concept behind the series, and why it's not equal to the improper integral, but the improper integral is adding up infinitely many values along this path. And so if infinitely many points in between converge to a value, then obviously if we're just taking a singular point along that way, it should also converge. And that's kind of the idea that goes into the integral test and whether or not it shows that our series is convergent. Okay, we'll talk about estimating what the actual value is eventually, but all we have to show is that the improper integral converges. If we do that, our series converges. We then know we can find some infinite sum. So we can either approximate it or spend time trying to find what it is exactly. And some pretty serious math thinkers have put in effort to find what some of these are, but obviously they don't have a method to solve all of them. They're kind of like treated on an individual basis. Now, what else I want to talk about with this thing is called what we call a p-series. This series that we're dealing with here is a p-series. A p-series is a series where basically we have 1 over n to some power p. That's what a p-series is. And so we see those in terms of, we have what we call the harmonic series. So that's like 1, 1/2, 1/3, etc. So that would be 1 over n. That's the harmonic series. This one here is just a p-series with power 3. But it could be any power we want, as long as p is generally considered like a positive value. So like 1/2 would also be a p-series. So 1 over n to the 1/2, that's also a p-series. But it's basically 1 over n to some power. It's not like we couldn't have like 1 over n to the -2, which would be an n squared. But we usually don't call this a p-series. We could maybe call this a p-series in this. It's just not very normal. You just often see these powers as positives. Okay, anyway. And the reason I'm just bringing that up is that when I refer to p-series in the future, this is why. Because it's a common enough series that it has a name. So, anyway. Okay, so determine whether this series is convergent or divergent. Okay, so we have this series from 1 to infinity of 2 over 5n minus 1. Okay, so I recognize that this is a linear, so integrating this isn't going to be too bad. So if we look at our f of n, first of all, f of n is a sub n, this like 2 over 5n minus 1. So what we're going to do is we're going to take the integral from 1 to t, limit as t approaches infinity of 2 over 5. I said that it doesn't really matter what variable we use. Technically the formula says x, but we can leave it in n. So in this case, I'm going to just leave it in n just to show you that it doesn't matter. Okay, so we're integrating this value. That's all that we're doing. We're integrating it from 1 to infinity, but it's an improper integral, so we have to take the limit as n approaches infinity. Okay, so the integral of this would be 2 times the natural log of 5n minus 1, because this is linear, then divide by 5. Now, if you don't really trust that, what I did was u sub. Okay, so that is to say, if u equals 5n minus 1, then du is equal to 5 dn. So we need a 5 in here, so we place a 5 and we pull a 1/5 out. That's where this 1/5 comes from. Then 5 dn becomes du, and this just becomes u. The integral of 1 over u is natural log of u. And this 2 was a constant multiplier. Okay, so just real quick, wanted to show that integral in case you don't see it. It's just a basic u sub. So this is our function here, or our integral. We're going to take it from t to 1 with the limit as t goes to infinity. So plugging in t, we get 2/5 natural log of 5t minus 1 minus 2/5 natural log of 5 times 1 minus 1. and we're going to take the limit as t approaches infinity. Now, the limit as t approaches infinity, this just becomes like minus 2/5 natural log of 4, which I don't need the absolute values. As t goes to infinity, 5 times infinity is infinity, minus 1 is infinity. The natural log of infinity is infinity itself, so it's 2/5 times infinity minus that, which is just infinity. So this diverges. So we know that by the integral test, this will diverge, so we know not to waste any time trying to find this infinite sum, the series, because it doesn't go to any value. It goes off into the infinites. We are adding infinitely many values here. Okay. Now, a few things to note is that even though logs are logarithmic growth, which is a traditional, I mean, if you think about logarithmic growth is very slow. That's kind of one of its purposes. It grows incredibly slow. But that does not mean that it doesn't grow for infinite, like forever. It grows forever. It takes a lot to see those same growths, but that's okay because in the infinites, they have a lot of growth available. So, it doesn't matter. It can go as far as it needs to see the growth that it needs. So this log, even though it looks like it maybe has some kind of horizontal asymptote, it doesn't. It grows off into the infinites. So that's why it goes to infinity there. Okay. Let's take a look at another one. Determine whether this series 1 over n natural log n cubed is convergent or divergent. And this is from n equals 2 to infinity. And the reason why is because natural log of 1 would be 0, divide by 0 would be a problem here. So this is one of those cases where, like I said, it doesn't actually matter that n is not 1 on our interval. Okay? Also, I've been neglecting to note that I take it for granted. P series here, 1 over x cubed, is a positive decreasing function. So this one was positive and decreasing over 1 to infinity. The one we just got done doing, 2 over 5n, 5x minus 1, is positive and decreasing over that interval. But here, for us, we have 1 over x ln x cubed here. Okay, now it is positive and decreasing, and technically speaking, it is decreasing on the interval from 1 onwards, but we're only looking from 2 onwards, and that is sufficient for us. Because, like, if we took this portion here, we could integrate from 1 to 2 and get an actual value, so it's like a solid number as well. So the integral from 1 to 2 of this exists, and it's a value. But anyway, we're just looking at 2 onwards, so it doesn't really matter. Okay. So we'll go ahead and integrate this thing. So this, we have 1 over n natural log n cubed. We're going to integrate this thing from 1, in this case actually from 2 to t, take the limit as t approaches infinity, dn. Again, I'm doing it in terms of n because why should I mix up the variables? It doesn't really matter. Okay, so looking at this is a u sub, so that is natural log of n is equal to u, so that means 1 over n dn is going to be my du. So 1 over n dn, we've already got those portions we need, so we can just throw them in. The limit as t approaches infinity of the integral from 2 to t of 1 over u cubed du. Okay, now if you notice, this right here is basically just that p series we've already done. 1 over n cubed. This is a 1 over u cubed. Basically the same, but now we're doing it from 2 to t. But that's okay. We did it from 1 to t and it worked out. So from 2 to t it should still kind of work out. But this is technically a u sub. But anyway, something to be aware of is that, hey, this is a p series. Okay. So Basically, all we need to do now is integrate this thing. This is just going to be u to the -2 divided by -2. And we're going to replace back. So you could technically have changed this, and in fact, when I change my variables, I often just drop the integration bounds, because unless I change them, it's not really true until I've changed it back. So I could change 2 using this formula. So natural log of 2 is u, so I could call this natural log of 2, and then natural log of t as t goes to infinity. That would also be an infinity. But if you're not sure, just leave it off, and we'll come back to it. So that means it's -1 over 2 times natural log of n squared. That's what we're dealing with, and we're doing this from t to 2, and the limit as t approaches infinity. Okay, so we'll plug that in. We get -1 over 2 natural log of t squared minus -1 over 2 natural log of 2 squared. Okay, so as t goes to infinity, this thing here goes to infinity. Squared, infinity. 2 times infinity squared is infinity. So we have -1 over infinity plus 1 over 2 natural log 2 squared. Okay, this is 0. And so we get 1 over 2 natural log of 2 squared. So thus it converges by the integral test. There we go. Okay, so again, this converges to a value. Cool. All right, so we can show that something converges via the integral test. But just because we know it converges doesn't mean we know what it converges, like what that series actually adds to be. But what we do is, instead, we think about an estimate. So suppose we're able to use the integral test to show that some series is convergent, and now we want to find an approximation to the sum of that series. So any partial sum, s sub n, is an approximation to the sum s. We call the infinite sum just s, because the limit as n approaches infinity of the partial sum will just be the infinite sum. But to determine how good the approximation is, we have to estimate the size of the remainder. So the remainder, what we call capital R sub n, is equal to the infinite series minus our partial sum, and it is basically every value after. So basically, this remainder is the error made when we use the first n terms to approximate the total sum. Now, let me explain what that means. If we were to find, let's say we have the first one we did was 1 over n cubed, okay? If we were to take a partial sum, n equals 1 to 3. Let's just do 3 because that's a nice manageable number. Okay, what that means is we're going to be adding 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed. Okay, so this third partial sum is an approximation. It's probably not a very good approximation, but it's an approximation to our total sum, the series, the infinite sum here, okay, because it's part of it. And that's what this is saying, is that it is an approximation to it, and it's an okay approximation to it because it is part of it. Now, the remainder would be all the parts that we didn't add. So that is a sub n plus 1, so in this case, a sub 4. So basically, the remainder is the rest of our sum that we didn't add in our partial sum. So that would be like 1 over 4 cubed, 1 over 5 cubed, 1 over 6 cubed, and so on and so forth forever. So basically, that's what this error is it's the infinite sum, so the whole sum subtracting off the partial sum, which we did, which is this black one. Okay, so that's what our remainder here is, and it's the error that's saying like how much off we are. So if we add up all of these values, the sum of all of these values is going to be the error. Okay, so this is our approximation. This is our error. And if we could add up each of these, we could find the exact error. But we can't because, I mean, that's the problem is that we're running into is if we could add up each of these terms individually, why not just add them all up? But we can use the same logic we just got done doing in our previous ones, which is, well, technically, this stuff here is less than just the integral from this point onwards, because the improper integral is kind of like the entire area, not individual points. All right, so anyway, so we'll talk about that in just a sec. So again, this remainder is the error made when we use our first n terms, okay? And so, like I've just got done mentioning, we're going to use the integral test to find a value for this, kind of an upward bound. But again, this is assuming that f is some decreasing interval on the interval, decreasing function on our interval. Okay, so let me show you what I mean by that. Is that basically, if we think about our remainder here, okay, our remainder is a sub n plus 1, a sub n, so that is a sub n plus 1 here, a sub n plus 2, etc. Okay? And that's going to be less than or equal to the integral from n to infinity, so from here to infinity. Okay? Because again, this infinite, or this improper integral here is taking like the area under the curve, and when we're adding our series together, we're just taking the individual terms, so we are definitely adding more stuff to it. And if we just kind of shift this curve over 1, then our remainder is also greater than or equal to the integral of n plus 1 to infinity. But to be honest, we don't really care so much about like what is our remainder in between. We usually just look at our remainder in terms of less than. So usually we're not as interested in greater than, we're just kind of more interested in less than. But if you notice, these are just our like left and right hand sums, basically. Okay. All right. So this is our remainder estimate for our integral test. If we have some function f of k and it's equal to a sub k, where f is a continuous positive decreasing function for x greater than or equal to some n, and the infinite series here is convergent, then if our remainder we define by r sub n is equal to our infinite series, the sum of our infinite here, minus our partial sum, then the integral from n plus 1 to infinity of f of x dx is less than or equal to the remainder, which is less than or equal to our integral from n to infinity of f of x dx. And like I said, in general, we tend to think more in terms of it being less than, because if, you know, we don't really, I mean, we might in certain situations care that our remainder lies between some values, but simply showing that it's less than or equal to some error rate is usually sufficient. But anyway, so again, this remainder here will just be the integral. We're just going to take the integral from our point onwards. So let me show you what that means in more definitive terms, because I know that the notation can be a little bit overwhelming. Okay, so we're going to use the sum of the first 10 terms to estimate the sum of the series and estimate the error as well. Find a value of n that will ensure that the error in the approximation is less than 0.001. Okay, now let me start with this thing here. This is called a p-series. Again, this is a p-series. Its power is 2. Now, this is something we're going to take for granted at a certain point, but I'm going to go ahead and tell you it now. Any p-series converges if our power here is greater than 1. So when we have a p-series, 1 over n to the p, if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. And we can see that through some really basic integration, but we've already talked about the harmonic series and the fact that it diverges. But 1 over n squared will converge, and I'll show you that in just a sec, because we'll do the integral test first to show that it converges. So, the integral of 1 over n squared from 1 to infinity dn. Okay? The integral of 1 over n squared, that will be 1 over, so negative 1 over n from infinity to 1. I know that technically it's from t to 1 and we're taking the limit as t goes to infinity, but I think at a certain point we can recognize that basically what we're doing is we're plugging in infinity into that thing. So I'm just going to do that. Negative 1 over infinity minus negative 1 over 1. So that is to say 0 plus 1. So it converges. All right, so this converges. So we know that because it converges, it's a convergent series, and so we can approximate the sum because it will actually be something. The sum is some value. Okay, so let's now talk about using the 10th partial sum to estimate it. What that means is we're going to take the 10th partial sum, that is n equals 1 to 10 of 1 over n squared, which means we're going to be taking like 1 over 1 squared plus 1 over 2 squared plus dot 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 until we get to 1 over 10 squared. That's what we're doing. And we can do that on Desmos very easily. You can also do it on TI-84 and things like that, but I don't have an emulator of that on my computer, so I'm not going to bother showing you, but it's in sums. But if you hit functions here on the keyboard and you go down to calculus, you can find a sum, n equals 1 to 10. And then you type your sum in, 1 over n squared, and we can get our sum here. Okay, so that's equal to 1.54976773117. That's what that sum is. And this, obviously, this is just part of our infinite sum, but it is approximating our infinite sum. So we're saying, it's about this. But approximations are only as good as as good as the error rate, basically. So it's important to note, what is our error rate? Well, basically our error rate is our remainder, r sub 10 here, which is less than or equal to our integral from 10 to infinity of 1 over n squared. So we just need to find this improper integral for the rest of it, from 10 onwards. Because we ended at 10, we're going from 10 onwards. And this is our upward bound. If we want our lower bound, we also know then that this would be the integral from 11 to infinity of 1 over n squared. Essentially, you know, we have like an upper, like a kind of, this is an under approximation and over approximation kind of concept or whatever. Okay. All right. So we don't really need to do this one. This is sufficient because, like I said, in general, we just care about some max error rate usually. But with the integral test, technically, we have a lower and an upper bounds, and that might be important depending on the situation. So we're going to integrate this thing from 10 to infinity. So that means we integrate this thing. The integral here would be negative 1 over n. And we're taking it from infinity to 10 here. And again, this is less than or equal to our remainder here is less than or equal to this value. So that is negative 1 over infinity minus negative 1 over 10. So that means our remainder is less than or equal to 1/10, or 0.1. Okay, so our approximation is 1.5, but it could be that it's like 1.649. But, I mean, depending on the application, that actually might be sufficient. So, again, this is kind of the max off it would be is 0.1. So, worst case scenario, our approximation of 1.5 is 1.6. Okay? But it might be, and it's likely, something a little less than that. So, again, depending on your application, that might be sufficient. But for our application, it's not. We want to find some value of n that will ensure that the error in the approximation is less than 0.001. So what does that mean? Well, it means that we just have to take n to be some higher number. So essentially, if we want to find exactly which one that is, we're just going to go to this statement here again. But this time, we want to actually solve for n. So that is, to avoid any confusions, let's call this x like we're supposed to. Okay. And we want to find the n that would cause our remainder, so that is this thing here, our remainder to be, I shouldn't have erased that, 0.001. So that is to say, our integral needs to be 0.001, basically. That's what we want this integral to be. Okay, so we're going to integrate this thing from n to infinity. Okay, so again, this integral is going to be, so 0.001 is equal to our negative 1 over x from infinity to n here. Okay, so 0.001 is equal to negative 1 over infinity minus negative 1 over n. So that is 0.001 is equal to 1 over n. This goes 0, adds. So multiplying by n times 0.001 is equal to 1. So dividing by 0.001, we get n equals 1 over 0.001, which is 1,000. So if we want to be that exact, we need to take our partial sum to the 1,000th. And hey, guess what? We can do that if we needed. That was too much. There we go. 1.6439. Okay. So this is now a good enough approximation for our needs. Okay. Again, 1.64, 1.549. So this is a little less than 0.1, as we saw, but it's pretty close to it. Okay. So that's all there is to it. Like I said, if we want it more accurate, well, we just have to take n out further. That's all. It is that easy. And it's actually really nice that we know that we can just, approximate it as needed. Because if you think about it, a lot of math in kind of real world applications of, like, at least in stuff like engineering and the sciences, tends to be as good as our measurements can be. So, in chemistry and in physics, we talk about our significant figures. And so there's no need for an approximation to be any better than we need. So if our sum, like our 10th partial sum, was sufficient, then fair enough, good enough. Now, one thing to note is that this p-series is about one of the first kind of convergent p-series that we deal with, and so it converges, but it actually takes a fair number of n's to get out to some point where we can be like more accurate. But depending on the series, you actually get like a 10th partial sum could actually be incredibly accurate depending on the series. So it just kind of depends on what you're dealing with. So this 10th partial sum might not seem like all that accurate in this case, but the 10th partial sum, depending on the series, could actually be super accurate. But again, it's only, your series approximations are only good if we can also find the error, because we want to know how close we were. Okay, let's do another one. So we're going to use this, we're going to take a look at that same one that we've already done, this 1 over n ln n cubed, okay, to find some value of n that will ensure that this error is an approximation less than 0.001. So that same statement, we're going to do the 10th partial sum. We already know this converges, so we don't have to waste time showing it converges again because we've already done this one. So let's take a look at this one. Now the problem with this one is that ln n cubed is actually going to be growing fairly slowly. So I actually expect this error approximation to be something pretty high in comparison. So we might end up with something ugly, but I'm just using one that we already did a convergence series for. Okay, so we are going to take the 10th partial sum because, again, we already know that it converges. So this converges. So that's going to be good enough for us. So we're going to take 1 to 10 of this 1 over n times natural log n cubed and find what that value is. And again, we're going to go over to Desmos for that. So 1 over, okay, ln n cubed. And we're going to take this from 2. I wrote 1, but I need to write 2. So it should be from 2 onwards. Okay. And we get 1.97551958194. And again, what we're doing is just adding these first 10, well, actually, technically speaking, so this is the first 10 terms, so actually I need to change this because n is 2. So if you think 2, I'm counting on my fingers, you can't see that, but 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's actually from 2 to 11. Okay, almost got me there. That's all right, I didn't change it that much. Okay, 1.9821130.921. Okay, so this is our approximation. Now, we needed to know, well, how good is the error? And again, the remainder, sub 10, is less than or equal to the integral from 10 to infinity of this 1 over x ln x cubed dx. I'm back to x's again, okay? Because we'll use n's later on, and I just don't want to get those mixed up. Okay, so we've already integrated this thing, but as a reminder, our kind of u here is ln x, our du then is 1 over x dx, and so we're basically just integrating 1 over u cubed. So that is to say, this is going to be negative 1 over 2u squared. So that is negative 1 over 2 natural log x squared. We're going to be taking this from infinity to 10 here. So this is our remainder, r sub 10, and it's less than or equal to that value. Okay, so plugging this in, again, infinity into this is just 0. So our remainder, sub 10, is less than or equal to 0 plus 1 over 2 natural log 10 squared. So that means that our remainder here, r sub 10, is less than or equal to this value, whatever that is. Let's see. 1 over 2 natural log 10 squared. Okay, 0.09. That's not horrible. 0.09. It's actually better than our previous one. 3, 4. Well, 4, 3, 0, 5, 8, 4, 8, 5, 0, 5, 8. Okay, whatever. That's our remainder. Not as bad as I was expecting. I was thinking it wouldn't be as accurate as our previous one, which wasn't super accurate, but actually it was. It's more accurate, slightly. Okay, so now this is our error, and maybe we're not happy with this. Maybe we want some error to be less than 0.001. So again, we're going to use the same concept where like r sub n needs to be, which is equal to 0.001. Okay, we want some n here, 0.001. We want this equal to the integral from n to infinity of this 1 over x natural log x cubed. We want this to be equal to 0.001, basically. That's what we're looking for. We want to find some n that will ensure this. Okay, so we've already integrated this thing. We can just go back to this statement, basically. So that is to say 0.001 is equal to kind of this negative 1 over 2 natural log x squared from infinity to n. So plugging in infinity, that goes to 0, minus a negative is plus 1 over 2 natural log of n squared, and this is 0.001. Okay, so we have to solve this statement. Okay, so 0.001 is equal to 1 over 2 natural log n squared. So the first thing I'm going to do is multiply both sides by this 2 natural log n squared. So we get 2 natural log n squared times 0.001 is equal to 1. And then I want to get this natural log alone, so I'm going to divide everything by 2 times 0.001. I know I can find what those values are, but I'm not going to bother until now. So 1 over 2 times 0.001. Okay, that's 500. So we get ln n squared is equal to 500. Okay, so now we have a couple options here. This is ln n squared. Okay, now basically, because this whole thing is squared, we can't apply our log rule to it, because it's like this portion is being squared is what the third log rule allows us to bring down. So instead, we're just going to jump into the square root here, and we get ln of n is equal to the square root of 500, whatever that is. Okay, now we don't need the plus or minus, because negative, our natural log here of n leading to some negative, we don't really want that. Like if we take a look at ln, well, I guess we could maybe get it. I'd have to think more about it. We can't log a negative, but logs can be negative. So like ln of, I don't know, let's just see ln x. Okay, so they can be negative, but notice that our n, they'd have to be less than 1, and for us, our n is obviously greater than 1. It's 2 and onwards, so it's not possible for our problem, so that's why we don't need it. I was going to say, oh, they won't ever be negative, but that's not really true. They just won't ever be negative on the interval we give a crap about. Okay, so it's only positive. All right, so now how do we solve for this n here? We take e to the power. So we get n is e to the power of square root 500, which is equal to e to the square root 500, a pretty big number. Okay, and that is what I expected to get something to be super accurate, is it would need an n that is huge. But again, if that is what we need, then it's what we need. And a calculator can still do it. It just might take a computer a little bit longer to compute that sum than, and you know, probably my calculator wouldn't do that. But who knows? Maybe it would. We can see. But 51418551478. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That was our 9. So this is what this is. This number n needs to be, and really, that means that we need to round this up regardless, because we need the error less than 0.01. So this needs to be a 48 here. 1558 1415. So pretty freaking big. N needs to be 5 billion. But again, you know, it's something that you could do if you want it to be more accurate. And the reason why it's so huge is because this natural log, these numbers don't get very big very quickly. And so you need really big numbers to make any kind of serious change to this thing. That's honestly the whole reason why. Okay. So again, just because it's some big number doesn't mean that that's a deal breaker. It just means that, okay, well, we might have to pull out the supercomputer or whatever for it. Okay. Let's do another one. Estimate this value correct to 5 decimal places. Okay, so this here I recognize as a linear to some power. So that's not really a big deal in my integration, because I could essentially choose 2n plus 1 to be my u, and then du would just be 2dn, something like that. So if we are integrating this thing, then we just need a 2 into it, basically. So the integral here from so first I need to make sure that it converges. That's my first step here. I'm just checking to make sure it converges. So from 1 to infinity of this kind of 1 over u, well, I'll write it as is, 1 over 2n plus 1 to the 6th dn. And so what we're doing is we're integrating that, and so like I said, it's just a u sub. So it's the integral from 1 over u 6 du. And we have a 1/2 because we needed a 2 in, so we had to pull a 1/2 out. Okay, now this is a p-series. Its power is greater than 1. It converges. But again, we can see that as well if we just integrate this thing. That would be negative 1 over u to the, so it would be 5u to the 5th. Okay, and it's times 1/2. So that means that this would be negative 1 over 10. And instead of u, we're going to go back to what we had, 2n plus 1. 2n plus 1 to the 5th. And we're taking this from infinity to 1. All right, so we're just, again, checking to make sure that this converges. So this is negative 1 over 10 times infinity to the 5th minus negative 1 over 10 times 2 plus 1 is 3 to the 5th. So that means 0 plus 1 over 10 times 3 to the 5th. And that does converge. But again, it converges as well by the integral test, but it also converges because it's a p-series, basically. Well, this technically isn't a p-series, but we'll talk about something that we can do in the future with that concept. So anyway, but this does converge. Okay, so now we want to estimate it. Now, there's a few things that we can do. Is we could just find an easy sum and see if that is sufficient for us. Like, that's all we need to do. If we want to find the exact sum that we need to find, then, we can do that as well. So that is to say, we want our error rate to be correct to 5 decimal places. Okay, so that is, we want 0.0000, so 1, 2, 3, something like that. So this is what we want, 5 decimal places. This is what we want our error rate to be. And so that is to say, this integral from n to infinity of our 1 over 2x plus 1 to the 6. We want this thing to be this accurate, and we need to find what that n is. So that's one way we can do it. The other way we can do it is just do an approximation, like the 10th partial sum, and see, is that good enough by computing its error. Like, that's always okay too. We don't have to turn this into some algebra problem necessarily. We could kind of just turn it into a guess and check. But it's all kind of similar enough processes that it's not really going to save me any hassle. 0.00001 is equal to, we've already integrated this thing, so I'm just going to pull up kind of this integral here. But we're going to take it here as our n, which is fine. So again, this is 0, and this would just be our n, plugging this n in. Okay, and 2n plus 1 to the 5th. Okay, so it's negative 1 over 10. Oh, I'm sorry. Really, it's this positive. So if we take it from, like, I'll just copy it and explain it. Rather than be lazy, I'm not going to be lazy. I want to be lazy. You can tell I'm really, really wanting to be lazy here, but I won't be lazy just to avoid any kind of confusion. But what I'm doing here is I'm taking this. I'm being moderately lazy. Okay, so we're taking this thing here, and we'll call that x just to avoid any potential confusions. Okay, so plugging in infinity into this, we get 0. Minus a negative 1 over 10 times 2n plus 1 to the 5th. So that means plus so 0.00001. So one thing to be aware of is just simply finding a partial sum and then determining its estimate might be easier for you depending on your problem. But this is easy enough to solve, so I'm just going to solve it like an algebra problem and find exactly what n we need. So if I multiply both sides by this bottom here, this 10 times 2n plus 1 to the fifth, then we get 10 times 2n plus 1 to the fifth times 0.00001 is equal to 1. So now I need to isolate this thing, so I'm going to divide everything by 10 and this 0.00001, which I know I could have just moved the decimal over, but whatever. Okay, 2n plus 1 to the fifth is equal to 1 divided by 10 times 0.00001, 10,000. Okay. So now, to solve this, we're going to take the fifth root, and it's only positive because it's an odd root. So 2n plus 1 is equal to the fifth root of 10,000. So 10,000 raised to the 1/5 gives us 6.3-ish approximately. And since we were looking at n's as whole numbers, I can just round it. It doesn't matter. So now we subtract 1. 2n is equal to 5.3. Divide by 2. So that is to say, so I'm going to subtract 1. And I'm going to divide by 2. And we get n needs to be 2.65. So that means, honestly, our n only has to be 3 to be that accurate. 2 won't cut it, but 3 will. So we could take our third partial sum, and it would be sufficient. Okay. That is, I mean, that goes to show how little of an n we sometimes need for this thing. So 2n minus 1 to the negative 6. 2n minus 1 to the negative 6. Was it minus 1? Have I been doing plus 1 this whole time? No, thank goodness. My brain just thought it was minus 1 at the end. Okay, I was a little worried there. Plus 1. Okay, so that is to say, if we take this partial sum, n equals 1 to 3 of 2n plus 1 to the negative 6, then we'll get this value here. And that would approximate it good enough for our needs, only using the third partial sum, which we could absolutely do by hand without any effort. So that's what I want to show, is that sometimes we might need an n to be incredibly huge, but other times we need the n to be pretty small and it will suffice for our approximations. And again, I mean, the fifth decimal place, that's still super accurate. I mean, correct to 5 decimal places, that's accurate. And so, you know, this third partial sum is all we needed for that. Realistically speaking, the reason for this is essentially because this power of 6 is so powerful that, you know, as we add additional n's, we're adding really, really small numbers as we go out. So for every one out, so 1, then 2, then 3, then 4, those make huge changes in the scale of this number. It makes it significantly smaller. And so basically, you know, at the fourth one, it's tiny, and we're just adding these tiny little bits onto it. So anyway, so that is our integral tests and estimates of sum. And again, the idea here is that we use the integral test. The integral test is a great tool if we can integrate them. So far we've been dealing with things that we can easily integrate. But if we run into series that we can't so easily integrate, then that's problematic for us, because we can't then use the integral test if we can't integrate it. So we'll have to use some other tools, and that's what our next lessons are going to be about. Thanks for watching.